Okay, everyone, let's get started. Sorry, I'm a couple of minutes late. So, as I mentioned last lecture, we're going to start the next lab today. Alex has passed out the boards, so we just got done assembling those. Hopefully, they're working. Let us know if you have any issues. So, I want to quickly go over quiz 2, and then I'll finish up the I2C lecture, and then I'll introduce the lab. And we can get started. So I won't take the whole time. So what's quiz 2 asked the question: what percentage of SPI channels master to slave bandwidth can be utilized in performing a series of write? Answer is 100% because when you're doing writes, the master sending the header and then the data on the master to slave channel, the MOSI channel. In a daisy-chained SPI communication between a master and n slaves, how many clock cycles are required to complete a full exchange? It would just be 8 times n, right? So if there's 1 slave, it's 8 bits to do an exchange. If it's 2 slaves, 16. What is CPOL and CFA for the exchange below? CPOL is easy. It's 1 because clock starts out high. And CFA is, to figure out CFA, you have to look at the data versus the clock. So with CFA, if the data and the clock change at the same time, CFA is 1. Right? Make sense? If the data gets a head start on the clock, then CFA is 0. You just have to remember that. What data is written in the transaction below? So we've got 8 bits of header, 8 bits of data. We're writing because MOSI is active. And so you have to basically separate the header from the data. And the only way to do that really is just count 8 cycles. So 1, 2, 3, 4, 5, 6, 7, 8. And then that brings us to here. I mean, you might be able to eyeball that and just kind of cut it in half, find the second half, but I'm not that good. So I'm looking at rising edges here, right? So I'm counting 8 rising edges. And then the second 8 rising edges will correspond to the data, which is 1, 1, 1, 0, 0, 1, 0, 1. Right. Okay, any questions? Okay, bus protocol requires 3 wires named DN, DOut, and clock. Is it a synchronous or asynchronous protocol? This is not a great question, but the idea is that there's a signal called clock, so it's reasonable to assume there's a clock as part of the channel, which would mean it's asynchronous. And then what bit is missing in the timing diagram below? This is a UART. So this is 5 data bits, which is kind of a strange way to do it, but it's 5 data bits, odd parity, 1 stop bit. So the first bit is the start bit. Remember that in UART, the default channel state is logic 1. So the first time you see the signal pull down, that's the start bit. So we have a start bit, and then if we look on the transmit side, you have a 0, 0, 0, 1, 0, right? So we're including the parity. So including the parity bit, there is 1 bit, right? And 1 is an odd number already, and so that missing bit must be a 0. Make sense? All right. And then for an SPI channel with CPOL equals 1 and CFA equals 0, when does the data signal change? CPOL means that we start out high, so the first clock edge is a falling clock edge. And CFA 0 means that we read starting on the first clock edge, so falling. Right? Okay, that's it. Any questions? Okay, we have another quiz that's due on Friday. So make sure you log in and take quiz 3 by Friday. Okay? All right, so then last time we talked about I2C and JTAG. So we're not going to have a lab on JTAG, unfortunately. Maybe someday we will. So JTAG we're just learning about for conceptual reasons. But for I2C, it's important that you understand this because we have a lab where you have to implement I2C. So I talked about how it's an open drain type interface where each device on the channel only has the ability to pull it down to 0, to transmit a 0. If nobody's transmitting anything, then the default signal state is 1, kind of like UART. Except UART's push-pull, but still it has a default state of 1 for some reason, right? But I don't know if there's a technical reason for that. But in I2C, there is a reason why the default channel value is a 1 because of that pull-up resistor, right? And that pull-up resistor can be internal or external. On these boards, still unclear, right, Alex?
It looks like it's on the IMU itself.
Yeah, oh, that's right. Our latest information is that this pull-up resistor is located on the IMU, the sensor. Not on the ESP32, and it's not on the board because we didn't put it on the board. The reason why we think it's in the IMU is that if you pull the IMU out, it breaks the I2C doesn't work at all. So yeah, we think that pull-up resistor is on the IMU. It's on the sensor, right? So there's this pull-up resistor, and then so that makes the signal there is a 1. And then there is normally with an I2C, there is some kind of a collision detect because it's a multi-master bus. So any host can take mastership of the bus. There is a chance that you'll have two things try to simultaneously take mastership, in which case there's a collision. And then if a collision happens, you have to back off. And generally speaking, if you have a hardware I2C interface, that collision detect is built into that. So in other words, it has to monitor what's going on as it tries to pull the channel low. In this lab, you don't have to implement that. You can assume that you're not going to have any collisions, right? Okay, so yeah, so basically it's just a pull-down type system, and that applies to both the data and the clock. These names, SDA and SCL, a little confusing. I don't know why they just didn't call it data and clock. But the DA stands for data and the CL stands for clock. And the S, I assume, stands for serial, but I'm not sure. And then the other thing is the protocol, the data is sent using a latch type system. So each bit is conveyed when the clock is high. During the time the clock is high, so it's a level sensitive system. It's not like SPI that's edge sensitive. This is a level sensitive. So you don't want to change the data while the clock is high. The presumption is that whoever's sending data is going to keep that data stable. The voltage of the data should be stable while the clock is high. So for example, the master, when it's sending, the master controls the clock. So the slave has to detect that the clock is high, and the slave will stop itself from modifying the data while that clock is high. It will actively prevent it, the slave will actively work with the master to ensure that the data stays constant when the clock is high. Make sense? And so the nice thing about that is it makes it easier to read these timing diagrams, because instead of looking for edges like you did with SPI, now all you have to do is look for when the clock is high, and you just look at the corresponding data value, right? However, the part that makes it confusing again, though, is the fact that when you're looking at the data, you don't know who's sending the data without looking at the context of the protocol, right? So remember that in SPI, the master was always sending MOSI and the slave was always sending MISO. Whereas in I2C, it could be either one. The master starts out by sending the address and the read-write bit. Okay, so that's 8 bits. It sends 8 bits. But then there's a 9th bit that's part of the header packet. That's the acknowledgement that's actually when the slave takes over, right? So the header is 9 bits and the data is 9 bits. The 9th bit on each one of those is the acknowledgement. But you don't necessarily always, so the acknowledgement is always the acknowledgement is, you always change hands. You change control for the acknowledgement. So the master sends the address, slave acknowledges, and then you may or may not change control once you get to the second half of the transaction, depending on if it's a read or write. So if it's a write transaction, the master will take over again and send the data it wants to write. If it's a read transaction, the slave will maintain control of the data pin and send the requested value back to the master, and then the master will take over for that last acknowledgement, right? So it's, you have to track what's going on in order to figure out who has control of the data in each cycle. Does that make sense? Okay, now for this lab, your code, you're going to be writing C code in the Arduino IDE that performs the master functionality, and the slave will be performed by the sensor, right? So you're going to be writing code that talks to the sensor using this, language, the protocol, right? And so as the master, you're going to have to toggle the clock up and down, up, down, up, down, up, down, right? And then you'll have to change the data in some cases and read the data in other cases, right? So that data is both an input and an output pin. Make sense? Mm-hmm. However, so you would think that you just mark it as bidirectional, right? No. Arduino still requires you to change the mode of the pin as you switch from reading to writing, even though it's open drain, which is really dumb. Shouldn't have, the whole point of open drain, right? You shouldn't have to do that, but at least with I2C, but you do. So there's two modes, and they're both described in the lab sheet. Let's see here. Yeah, so there's a mode called output open drain. So when you want to drive a pin, remember there's two pins, SDA, SCL. And those pin numbers are listed in the lab sheet. And in this case, I just have a define for those, right? So I just refer to SDA and SCL as symbols, right? And so you set the pin mode to output open drain when you want to drive. And when you want to read the pin, you set it to input pull up. So output open drain and input pull up are the two modes for the pin, depending on whether you want to read or write. And obviously you're going to have to change those within a single transaction, right? And then there's a digital write and a digital read function. Okay, make sense? You guys, have you ever used that before? These are just standard Arduino, digital read, digital write.
Never used Arduino code, but it looked similar.
Similar to 313, yeah. Okay. Okay. So we have, so that's the way that you read and write I2C. Now, there is a separate protocol for the sensor itself. So this is where things are a little weird. So I talked about how all the examples I've shown you with I2C have been a single, I said you send an address. I didn't really say what that address was meant to signify. You probably assumed it was like a register address, right? Like with programmed I/O. And then there's a single byte of data. It's a little different with this sensor, the way the sensor works. So the problem with I2C is that it's meant to have multiple slaves. And you can have obviously multiple masters. But the presumption with I2C is that you got a whole bunch of things attached to it, right? Now in this lab, we don't. We just have one thing attached to it. There's just the one sensor. But if you do have multiple things attached to it, the address is generally used as a way to target a specific peripheral. So it's a way for the master to identify which slave it wants to communicate with. So in the case of the sensor that we have on the board, it has a device address. And so every time you communicate with it, that address field is going to have the same address in it. Okay? So then you might say, well, yeah, but then how do you then determine which slot on that device you want to read or write to? Like what is the control register and the status register address? Where do those go? Okay, so where that goes is when you write, you write the device address first, right? Then you set the read-write bit to be right. And then in the second 8 bits that you send over, that is going to be the register address on the sensor you want to write to.
Okay, and it knows to...
And it'll recognize that, right? And then you send another group of 8 bits, right? Right? So what ends up happening is that this whole thing gets changed. This is just showing 2 8 bits, right? When you write on the MPU, there's a third 8 bits, right? So you maintain control for a third, and then you write the data, you send the data you want to write.
Okay.
Make sense? So you write 3 bytes. You write the device address, the register address, and then the data you want to write in that register. You only have to do that one time in this lab, though, because the only time you ever have to write to the sensor is when you send its initialization. There's a Alex, what is it? It's like a setup register, basically. You just set it up.
Power management register.
Power management register, yeah. There's some fields in the power management register you set. So you only do one write, and you can do that in the setup section of your code. Make sense? Obviously, with a sensor, you're going to spend most of your time reading, right? You're reading these accelerations, right? Okay, so how do you read? Okay, so for reading, you start out the same way. You write the device, you send the device address, right, in the header packet. And then, of course, the read-write is set to write, right? Now you might say, well, wait a minute, why would you write if you're trying to read? Well, what you're going to do is write an address register on the sensor is what you're doing. So you're going to start out by, you send the address of the sensor, then you send, and you tell it to write, and then the data you write is going to be the register you want to read from, right? So think of it like there being a slot on the sensor that holds the address of the register you want to read from, and you have to write into that slot, right? So you tell the sensor, get ready because I am going to read from address 10. So I will then put 10 in the data field of the transaction. Okay? Then you close down the transaction. Then you're done. You cut. Then you have a follow-up transaction where you send the device address again, but this time the read-write bit is set to read, right? And then on the second byte, the device is going to send back the contents of that register, right? So what I'm saying is, to summarize this, when you write to the sensor, it's done in one I2C transaction consisting of 3 bytes, right? Device, address, data, right? But when you read, you have to do it as 2 separate transactions. The first transaction sets up the read by sending the address that you want to read from on the sensor. And then the second one actually allows the slave to send the value back to you, right? But both of them have the same address, which is the device address. So you write to the address of the device with the register address, close down the transaction, and then you do a read from the same address, and you'll get the results back. Does that make sense? Okay, it's all described. It's described in the lab sheet, and I tried to show how that works. But that's basically the protocol. Okay. So what are we going to read from this thing? Well, as I mentioned, it has a gyroscope. It has a 3-axis gyroscope, a 3-axis magnetometer, a 3-axis accelerometer, and it has a temperature sensor for some reason. So our goal is to read just the acceleration. The problem is that the acceleration is in 16 bits. It's a 16-bit acceleration. And I2C is 8 bits, right? So that's a problem. So in order to read one of the 3 axes of the acceleration, you have to do 2 reads. You have to read the high and the low part, right? And then there's 3 axes. So in order to read all 3 axes, you have to do 6 reads. And remember that each read requires 2 I2C transactions. So you have to do 12 total I2C transactions in order to read the 3 acceleration values for x, y, and z, right? So that's going to give you the acceleration in the 3 axes. And then what are we going to do with that? So what we want to do is we want to determine what the tilt of the sensor is. So if the sensor is sitting level to the ground or like the center of the earth, you're going to see 1 g of acceleration on the z-axis. I guess negative 1 g, right? It would be negative 1. Okay. So the scale is plus or minus 2 g's, and it's expressed over 16 bits, right? So what that means is that, remember, a signed and it's signed. So a 16-bit signed number has a range of negative 32,000 to positive 32,000, right? Negative 32K to positive 32K. And that's meant to represent negative 2 to positive 2. And so if I've got 1g of acceleration, negative 1g, then if I have the thing level and I read the z-axis, it should be negative 16,768, because that would represent 1 on the scale of plus or minus 2, right? It would be negative 16,000. That should be 1g. Now you can change the scale, by the way, but the default scale is plus or minus 2, and we just assume that you're going to leave that as default, right? You can also do plus or minus 4, 8, and 16 as well, but the plus or minus 2, I think, is fine, right? Okay, so what you should read when the thing is level is negative 16,768, ideally, on the z-axis, and 0 acceleration on the x and y-axis, right? But what we want to do is convert that to a tilt angle. So the idea is to conceptualize this as 3 planes. There's an xy plane, an xz plane, and a yz plane, right? And ideally, we should be able to measure the tilt, the tilt of each of those planes, right? So, so how do you do that? Well, it's pretty simple. We put a formula. It's basically arctan 2, right? You just calculate the arctan 2 of 2 of the accelerations, and that'll give you the tilt angle, right? So the idea is that these 2 planes are the x, like if you have this thing level, the xz and the yz plane are going to be pointing straight up and down. They're going to be like this, right? So they'll both have a 0 angle. And then the xy plane is like this, which should give you a 90-degree angle, because if this would be 0, right? If you had it tilted up like this, it would be a 0. If you tilt it like this, which is meaning that you have it sitting on the desk, it's level, that's going to be I think it's negative 90 degrees actually is what it prints out, negative 90 degrees, right? So you might say, well, why do we care about angles? Well, the ultimate goal is to try to make something that balances. We want to try to make a balancing robot, essentially. And so we care about these angles. We want to try to keep this thing in equilibrium, like have it balance. So that's why we're converting these accelerations to angles. But the calculation is trivial. That's not the hard part of this lab. That's like 3 lines of code. The hard part of the lab is doing the I squared C, and that's the point, is understanding how I squared C works. Make sense? And so this is bit banged, obviously, so you're going to be using digital read and digital write to implement I squared C. Now there is hardware in the ESP32 for doing that, but that doesn't help you understand. If you use that, you don't understand how I squared C works. Okay, any questions? Okay, so we have, if you look at the lab sheet, we have a rubric there. This rubric is very extensive because I try to put in all these different sort of partial credit scenarios. But ultimately, if everything is working and you demo it, you should just be able to show us, the board, and you should be able to tilt it, and it should just print out the angles on the console, right? Any questions about that? Okay, so to get started, I haven't talked a lot about the Arduino IDE because you might remember that when I taught 611, I showed a lot of screenshots and stuff from Quartus and all that stuff. Arduino is pretty simple. You just type Arduino, right?
I think you type Arduino-IDE.
Okay, Arduino-IDE. It should be installed on the lab machines. Alex wanted me to mention to you also that you can install it on your home, your laptop too, if you want, and use the boards with your own laptop. But we ask that you...
It's not like Quartus where it's a huge pain. It's super easy to install.
Yeah. In fact, we used to use, up until last time I taught this course, we were still using Quartus in this class. So this is the big change we're making, is trying to move away from Quartus. It's overly complex. So type in Arduino-IDE, plug in the board, and it should be ready to go to start coding. All right? If you need any help, let us know. Soyash, Alex, or me. And by the way, the other thing too, and I might want to do I'll save this for next lecture, Thursday. Might want to do a quick tutorial on the oscilloscopes.
Oh, yeah. Yeah, I was just figuring it out right now.
Okay. So the oscilloscopes, so as I mentioned last lecture, debugging is going to be a challenge with this lab. You can use print debugging, but you can't actually freeze the code in the debugger as you normally could, right? Even on the Quartus, on the FPGAs. So if you have trouble with communication, one way to diagnose it is to use the oscilloscopes and probe. We have put on the board for you test points. If you look at the bottom of the board, there's little headers that stick out. And there's an SDA and SCL test point. So all you have to do is clamp those test points with the probes of the oscilloscope, turn on the oscilloscope, and you can see what's going on there. Right? And then there's also an I2C decoder built into the oscilloscopes, which you can also use if you don't want to try to read binary data. If you want to see if the scope can interpret what's going on, that's also available. You just have to set up the decoder.
You can also use the digital probes. That's easier because you don't have to. You can just plug those straight into the header instead of having to clip onto the sides.
Yeah.
So
Yeah. Oh, okay. Yeah. Then you got these 16.
Yeah,
you have a 16-legged octopus on your hands with that. But yeah, that works. Okay. All right. Sounds good. We'll just let you. Well. Oh yeah. Oh, Alex. Sorry. One other thing I forgot. Almost forgot. Alex is going to walk around and he wants to blow the fuse for, what is that again?
Yeah, so all ESP32 boards by default, they have a flash chip on them that basically it's the flash memory that holds all your code. And that flash can either run off of 1.8 volts or 3.3 volts, depending on the ESP32 model. And in our model, the flash can only run off 3.3 volts, but it's configurable by the state of one of the pins at power one time. So when the ESP32 is installed into our board, there's a chance that pin is going to be in the wrong state at power on, which would lead to the flash being powered up in 1.8 volt mode instead of 3.3 volt mode, which will cause your ESP32 to not boot. So we need to bypass that pin and hard code it so that it always boots up in 3.3 volt mode. And you do that by blowing a fuse inside the ESP32 that permanently bypasses that. So I'm just going to go around and blow everybody's fuse while you're working. And yeah.
By the way, the reason for this is it's because we're using every pin.
Yeah, it's because we're using every.
On these boards we're using every pin, and you might say, well, come on, it's only 2 pins for I2C. The motors, we have 3 motor connectors, and the motors are using most of the pins because the motors are pin hungry. And then of course we've got the speaker and the I2C and the LEDs and stuff like that. But most of the pins are taken up by the motors that ultimately we're going to use to try to keep the thing balanced. We're using centrifugal force. So that's the reason why we have to do this. We couldn't tie that pin low on the board because we needed every last pin.
Yeah, exactly.
Okay. Thank you.